Hello everyone, today we will talk about our term project which has three parts. So for part B is a buck boost converter design. Here is the requirement and the specifications. So firstly, we will look at the buck boost converter circuit which is shown here. So from the circuit we have to know that we need to calculate several parameters: duty ratio, inductor, capacitor, resistance, load. How to calculate these parameters? Using the equation from this slide, you can see that duty ratio is equal to 0.4, and as input circuit ripple less than 0.25, we got the inductor value, which has to be larger than this value, and we choose L equals to 5. And with calculation, we got R, the load, which is equals to 8, and we also choose the capacitor. So in this slide, we calculate all the parameters that we need. Okay, for simulation, we put all those values inside. Here is the inductor, current, load, and we have to remember that here we need to set it at crossover frequency, which is 50 kHz. This is for the PWM. Okay, so here is the result. As we can see from here, the Vout value is great, and inductor value equals to I in minus I out. This value looks good. If we zoom in, it looks like this. Okay, then for part B, we will design a boost converter with a feedback controller. The difference between the feedback controller is that it divided into several parts: controller, PWM, power stage. And we also have to set the KFC. You will see from here, as there is the deserved value, and using this feedback compare with the necessary value, you will design how to control this loop. Okay, so step 1, we're gonna design PWM. We set VR equals to 1, so got this value. And step 2 is power stage design. Using duty ratio equation we got, which is equals to 0.6. And with LE equals to this, we choose L equals to 40. Got this value, and this equation for power stage transfer function, we can easily find it on notebook. So put all this value inside this, we got the transfer function of power stage. And using MATLAB to got the body plot. As we can see from this body plot, when we at the crossover frequency, which is equal to 5 kHz reds per second, we got the magnitude equals to 88.1 and the phase margin around 92.2. Okay, it looks good. So we got these two values which we're gonna use later. Okay, so step 3 for controller. So we got this equation for controller, the transfer function. This Kc omega z omega p is the value that we need. As the desired phase margin is equals to 60 degrees, we got the boost, the phi boost. And then using this equation, which is equals to 1, we set KFB equals to 0.2. We got the transfer function at crossover frequency. And here is all the parameters for how to calculate them. We got all these parameters. So we got the transfer function of GC, which is the controller transfer function. Okay, and we put that controller transfer function into the MATLAB. We got the phase margin here is 90 degrees, which is larger than 60, but it's okay. Here is also the body plot for circuit transfer function. And next, we're gonna design the op-amp design, which we will use it exactly in the simulation. So we choose R1 equals to 100 kilo, and using the equation from Notebook 4, Chapter 4, 4.31, we easily got these values, and we will put this value in this op-amp loop. Then we will start our simulation. As the requirements, we have to set the loads with different values, divided by 2, multiplied by 2, and then as the results shown from here, we can easily find that the output voltage is almost not changed, almost stable. Only the time, which is need to got the peak value, changed a little bit, and the time for stable changed a little bit. Then we will move to part C, PFC circuit design. For the difference between PFC circuit design and the boost converter with feedback controller part B, we have to design also the circuit controller and the voltage controller. For the circuit controller, we already discussed, which is similar to part B, so you can just easily follow this step part B, got this value, and here for part C we will mainly talk about how to design the voltage controller loop. For voltage loop design is shown as follows. We got this equation from Notebook, and then combine the equation chapter 6.1. We got all these values, and then put this value inside, and put this value inside the voltage controller transfer function. To finish the simulation, we put all those values inside. So here the most important part is the voltage